Good morning, or good afternoon, good evening, whatever it is for you. My name is Pau Amaro Seoane, and I'm going to make a summary of what conformal diagrams are. I am not an expert on this, but I think I know a couple of things, and I would like to do this because some students require this from me after a course that I gave on gravitational-wave astrophysics. So these conformal diagrams are very powerful because they allow you to see what happens in a space-time, which might be flat or not, and they even allow you to intuitively understand what happens when you cross the event horizon of a black hole. So I'm going to first start introducing regular standard space-time diagrams. I will then move to flat space-time and then introduce conformal, or if you want, Carter-Penrose Carter diagrams. And then we will start studying the interior of black holes. For this, first we will commence with Schwarzschild black holes, and then we will move to Carter black holes. I don't intend to do everything in a single session because this would take too long, and yeah, I don't know. We will see. I will start today with space-time diagrams because they are very important and they allow us to introduce the notion of a light cone. I think that everything that I'm going to say is correct, but if I make a mistake here or there, which is very likely, I would not have any problem. On the contrary, I would be very thankful if you pointed to me to that mistake. Okay, so let us start first with these space-time diagrams. I have here some drawing software. Okay, I have to rotate this thing, this iPad, but of course now it is not working. Maybe it will work now. Okay, there you go. So let us start with two axes. Okay, looks like a good thing to do. So I'm going to draw here one axis and here another one, because we love Cartesian axis. I'm going to even add the head of an arrow to give you the flow or the sense, not just the direction. And being extremely original, I'm going to call this coordinate x. Okay? And here we're going to have t, time. But I want you to understand the following. I'm going to be assuming, actually I'm not, it's not time, it's time times c. But I am setting c equals to 1. Why? Because it's useful. You will see that. Okay. So this is time multiplied by c. Now, if I draw a line in which I have this axis, so the y-axis equals to the x-axis, I have this line, and the same thing here for negative values of x. Okay? Now, the most important thing is this angle here. This is 45 degrees, obviously. This is 45 degrees because, of course, this is 90 degrees. Okay? So, that thick line, so that these 4 lines that we have drawn here, these 4 thick lines correspond to C equals V. So your velocity is the speed of light. Okay? So anything that happens in our universe is contained between those lines. Let me look for a nice color, like this one. So our universe, where you and I live now, happens here, in this line, in this region, sorry, with the boundary, those thick lines, and in this region. This is it. This is easy to understand, right? Now, if on the contrary you happen to be outside of those lines, you're here, okay, in this blue area with the boundary the same line. Now, in this boundary, in this region, we have that any value that the speed is taking must, by definition, not by definition, by derivation, be larger than c. That's easy to understand, I guess. Let me pick up the correct color, which of course I will not be able to do. Maybe here. Okay. So outside of this orange region, we have that the velocity is larger than c. And in the orange regions, like here, we have that the velocity is less than c. And in the thick lines, as we have seen before, c equals v. So we're moving at the speed of light. What does this mean? That means that only massive particles are moving at the speed of light, like photons, and they are the only particles, whatever a particle is, by the way, because I don't know that. It means that only particles can reside, if you want, on those lines, on those thick lines, with an angle of 45 degrees. Now, because on the bottom the time is negative, this is the past. Here at the center is where an event is happening, like the starting of this video. So it is the present. T equals 0, if you want, now. And on the top of it, of course, as you can guess, we have the, sorry about that, future. Okay? Now, it is important that you understand this. I'm going to make a break now to delete all of this and make a nicer plot. Wait a second. Okay, we're back. I have simplified a little bit this thing. So again, on the top of the plot, of course, we have the future, and here we have the past. Now, because nothing can move faster than the speed of light, we call this the area enclosed by the light cone the causal region of this space-time diagram. And because nothing can move faster than the speed of light, at least not in our universe, these weight areas are non-causal. If you lived here, very strange things would happen. Like, for instance, I don't know, you could call the elevator, and the elevator would get to your floor before you pressed the button, and these kind of things. Okay, and I am spending so much time with this because it is crucial that you understand the following. It's all about these 45 degrees. If your light cones, because these are light cones, there are cones of light, cones with a boundary that defined by the speed of light. If your cones have a slope at most of 45 degrees, then you are causal, okay, in the future or in the past. If your cones have a slope larger than 45 degrees, like this, or this, or this, or this, then you are non-causal. You cannot exist. Whatever you are talking about does not make sense in our universe. Now, we're going to take a look now at exactly the same plot, but with 3 dimensions. And things are going to be slightly different. And it is not trivial a priori what is going on, and this is why I'm going to take time to make again a beautiful plot. Here we go again. We have an empty sheet of paper. It's not paper, but anyway. And I'm going to do the same thing. This is going to be time, again, t, but please remember that we are setting all the time c equals 1. And here we have the radius. We want to work on spherical coordinates because I'm going to assume spherical symmetry. Okay? Spherical symmetry means what? It means the following. This is a sphere, and you know what is the relation between the usual Cartesian coordinates and those of the sphere, right? So we have x, y, z, and any point on that sphere is described by a vector of length or modulus r with projection on this axis like this. Okay? So that we have 2 angles, theta, or in ancient Greek, theta, and I, or in ancient Greek, pi. P, describing your point in a unique way, which is this one here. Okay, so the question now is the following, and I have seen many students not understanding this, which is why I want to really stress this out. If you are sitting at t equals 0 and you switch on a light, that light is going to move with a slope of 45 degrees, right? Like this. We have talked about this already. It must be 45 degrees. But of course, you could do that at a different place, like at your office, or much better, at a bar with your friends, etc. Right? But if it's light, it must move with a slope of 45 degrees, 45 degrees, 45 degrees. Okay? Now, the same way, okay, no, let me back up a little bit first. So if you could live forever, and you could observe the trajectory of these rays of light forever, all of them would define at infinity a kind of surface like this one at infinity, which is what we like to call a null surface. Now, I am being extremely hand-waving here because in order to bring that infinity back to the sheet of a paper or, you know, the screen of whatever pad you're using, you need something which is a conformal transformation. Conformal transformation. And this conformal transformation is something quite complex, at least for me, and that I might or might not describe later on when I move on with this video. But in any case, as for now, the only thing that I want you to understand is the following. All of these, if you want, outgoing rays of light, and I'm calling them outgoing because, you know, time is going like this, and the radius is increasing in that direction. All of those outgoing rays of light are defining at infinity a surface because we're talking about 3 dimensions, right? R has 3 dimensions, which we call a null infinity surface, okay? And guess what? That null infinity surface is going to have a slope of 45 degrees, okay? So this is a null infinity surface. Okay, but the same way that we have these outgoing rays of light, we can also have incoming rays of light, right? So if someone at infinity decided to switch on their lights and send us a signal, these signals would come to us like this, right? And this allows us to define, surprise, surprise, an equivalent to the upper surface, but for negative radii, of 45 degrees. And that is going to also be, oops, sorry, no, not this one, a null infinity surface, Okay? Again, it is very important that you understand that these are 45 degrees and are 45 degrees. Okay? Because, well, we have here these incoming rays of light. Now, the usual question that I ask to students is the following. If you have one of these incoming rays of light, what is going to happen when they hit the time axis? So, imagine the following. You have an incoming rate of light like this one, and it reaches this axis. So what is going to happen to that ray? Maybe, if you want, you can now pause the video and think about it before I give you the answer, because that would be the correct thing to do. I'm going to give you like 3 seconds to think about it, whether you want to do it or not, and then I will give you the solution. I'm going to delete this now to give you the solution. So what is going to happen to an incoming rate of light which hits the time axis? So I have heard all kind of different answers, like it's going to traverse it, it's going to be deflected like that, it's going to follow the time axis upwards. All of those are obviously, well, actually not obviously. I apologize for that, because there's nothing obvious in life, and sometimes one can be a little bit mind upset. What is going to happen is the following. Remember that we have a spherical symmetry. But that means the following. Let's go back to one dimension. This is the x-axis. Okay? This is 0. This is 1. This is -1. This is 2. This is -2. This is, by the way, why we have complex numbers, because for one of these numbers you have a companion living 180 degrees on the other side of the line. Okay, like 1, 2, etc. So if we are moving in that direction, at some point we will cross 0, and we will keep on moving. There's a minus missing there. Okay. Now, because we have spherical symmetry, imagine the following. Imagine that you have a star like our sun, or any other star you prefer. I like the sun very much. So let's take a star like our sun. Look at this wonderful star. Okay? And this star has a center, which is located at at r equals 0. Now, you have an incoming, an incoming photon is probably a bad idea, because they're going to be deflected by interacting with other particles. Let's have an incoming neutrino from outer space passing through the star. This incoming neutrino will reach 0, the origin of the star, and of course it will just keep on moving after that, right? And it will cross the star like this. So it will first cover the first part, sorry, that was wrong, the first part of the radius of the star, and then from here to there and then it will cover the remaining part of this star. Okay, and 0 is located here. There is nothing special about 0. So when you translate this into the kind of diagram that I was talking about before, and this is the answer, you represent it like this. This is radius, 3 dimensions, and this is time. So when you have an incoming rate of light, it will reach 0, and because it cannot go to negative values of 0, because negative distance does not exist, of course, it will just follow that trajectory. Okay. I hope that's clear, because very, very frequently this is not clear. Okay, let's move on. I'm going to clear the whiteboard now. Okay, so we're going to start talking about a flat space. Okay, so we have our axis again. This is time here. We have here radius, and we have here these surfaces, which I called before the well, they should be exactly, hitting the same point, but well, you get what I mean. And we have here null infinity surface, and here as well, null infinity. Now, this is the past null infinity, and this is the future null infinity surface for obvious reasons. Please remember that it's going to take an infinite amount of time for you to reach to that line. The same way that anything coming out of here will take an infinite amount of time to reach you. Now, the very interesting thing about conformal diagrams is that what we discussed about before, the light tones, they are preserved here. So if you want anything to be causal in your flat space universe, it must be contained in a 45 degrees cone like this. So any event, like for instance this one, must be contained in a 45 degrees cone. What does this mean? This means the following. If your life starts somewhere here, this is you being born, you will have, an interesting plain life, and at some point you will die. But at any given moment of your life, all of your future, as well as all of your past, must be contained in a cone of 45 degrees. Okay? There is nothing which can have a slope larger than 45 degrees. Now, there are a couple of interesting points here that I want you to draw your attention to. I'm going to change the color because it's too black, like red. This one here, this one here, and this one here. Okay, so this point here, the red one on the right, is what we call a, I'm going to make some room. This is what we call a space like infinity. Okay. And this one here is a time like infinity, like this one on the top as well. Okay? Just remember that because it's important. I will explain more about these things later. An important thing that I wanted to mention is the following. Imagine that we have an observer, and for this I'm going to delete everything now because this is getting too crowded. Imagine that we have an observer, a god. You pick up any god you prefer. I don't know, God, Buddha, Allah, it's up to you. Depending on your religion, if you have one, which is going to live forever. Okay. So we have our flat space-time. Remember that this is flat, and the trajectory of this eternal person in this flat space would be something like this. Would start at the bottom, time like infinity. I would reach the upper time like infinity point. Now, this person, of course, I was making a joke when talking about the gods, because I needed somebody with an infinite amount of time at their disposal, can try to accelerate, okay? And unless they do something very, very special, they will start here and they will end up here. Now, if you want to accelerate your motion, what you have to do, remember, is to try to get to a 45 degrees slope, so that this person, whatever this person is, what they should try to do is to get closer and closer to that slope, okay? But it will never reach it, because for that you will require that the speed of this person is higher than 45 degrees. Another important point before I finish with this first video, because I think this is a good moment to stop this, is the following. And for this I have to delete a little bit here and here, these drawings, is the following. So surfaces, because we're talking about 3 dimensions, surfaces of constant radii have this shape, this diagram, okay? And this is important for what I will explain later. And there is something important that you must understand here. These conformal diagrams, they depend on the coordinates. But there is one fundamental coordinate here, which is the radius. I will talk about this later. In the next video, I'm going to discuss something different. I'm going to stop now the sharing of this screen. So, in the next video, I will discuss something more interesting, which is the case in which you have a Schwarzschild spacetime in vacuum without any kind of source terms, because we're going to go step by step, increasing the difficulty of the problem. We have started with a flat space, and the next thing that we're going to do is to discuss Schwarzschild spacetime vacuum. So that if you look at the Einstein's equations on the right-hand side, you have 0, and we're going to assume perfect spherical symmetry. So when we are very, very far away from the black hole, if you remember in those null infinity surfaces, they're going to be the same. Why? They're going to be the same because you do not feel the, as they like to call it, overwhelming pull of gravity of the black hole, because you're at infinity, and that part of the diagram is going to be exactly the same. So the null infinity size of this diagram are going to be exactly the same, because as we know, for instance, in our own Milky Way, it is very likely that we have a supermassive black hole. Last year, the Nobel Prize Award went to the discovery of a supermassive dark object at the center of the Milky Way, because thanks to the, in this case, yes, impressive work that observers have been doing for the last 2 decades, they have observed that there is a very, very deep potential well located at a radio source which we call Sagittarius A star. And when you look into it, you see something that should not be happening. We see that stars are moving, and as far as I know, when I look at the sky in the night, stars are not moving. And I can go to the same place on holidays and with my partner and say, look at this wonderful constellation. It's called Orion. I actually don't know where Orion is, but I know there is one constellation with that name. Look at that other constellation. Look at that other constellation, etc. When I retire and go on pension, I will go with the same partner, maybe another one, or the n+1 partner, I don't know, to the same beach and say, look, that's Orion, and Orion's in exactly the same place as so many years ago, etc. When I die and the children of my children go to that beach, Orion will be on the same place. So stars do not move. But if you look at the galactic center, there is a group of stars, actually very interesting stars, because we do not understand why these stars are there. They should not be there, but this is a completely different topic. When we look at them, they move very quickly. They change their positions in a matter of a few months. And thanks to the motion of those stars, which are revolving around one point, and thanks to those stars, thanks to Kepler, and thanks to some post-Newtonian corrections, we have derived the mass of the object that they are revolving around. And it is of about 4 million of solar masses, enclosed in about 22 millions of kilometers. 22 millions of kilometers sounds like a lot, but it is not, because a galaxy has a size of about a few thousands of parsec. A parsec is a unit. something like of about 3.3 light years. Okay, a unit. You can, you can call it whatever you want. You can call it a cucumber. Okay, a galaxy has a size of a few thousands of cucumbers. And when you look at the size of a black hole, if you identify the size of that black hole with the spatial radius of the black hole, there are about 10 orders of magnitude of difference in length. So a 1 followed by 10 zeros. So a black hole, although it might be very strong, etc., has a very small radius within which you can call it overwhelming. In the case of our own Milky Way, that radius, which we call the radius of influence, is of about 3 parsecs. Okay. So in any case, because we are so far away from the black hole, that part of the diagram, the null infinite size of the conformal diagram, are going to be the same. But as we get closer and closer and closer to the black hole, something very interesting will happen. And when we cross the event horizon, things are even more interesting. But we will go there step by step. If you have any questions, you can send me an email at my email address, obviously, which is Amaro, like my surname, at riseup.net. Thank you, and bye-bye.